Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking a look at the opposite of derivatives, integrals. Now this episode is more geared towards the integrals that you might see in a physics class and the properties and rules that you might need there as well. And it's also going to set us up to be able to solve some of the problems that we're going to see in future episodes. It's not going to be a deep dive into the actual mathematics of what integrals are and that sort of thing. We'll do that at another time. Integration is the opposite or inverse operation to differentiation. And whereas a derivative is analogous to a slope and therefore sort of analogous to division, integration is analogous more to multiplication, or a series of infinite summations of infinitely small chunks of a function. To begin, let's look at the fundamental theorem of calculus to kind of illuminate some of these ideas. The fundamental theorem of calculus states that for a function evaluated at its endpoints, the difference between the outputs at those endpoints is equal to the integral of that function's derivative evaluated from one endpoint to the other. That's a bit of a mouthful, but let's break that down. So if I take the outputs of a function, capital F in this case, at these endpoints A and B, if I then take the derivative of capital F, which we're going to call small f, and I take the integral of that derivative from point A to point B, I get that difference in the endpoints. We'll come back to that in just a second. But taking a look at this notationally, we can see that we have an integral symbol here. We have an integrand, which in this case is lowercase f of x. And we have limits of integration, which are a and b. Also, we have an integration element, dx in this case. X is our variable of integration. Thinking of this as a type of multiplication, we can see that this is sort of like multiplying the outputs of lowercase f times infinitesimally small chunks of changes in x, which is what dx represents. If I take all of those multiplications together and then sum them all up, which is what the integration operation does, we get our parent function, capital F. In this way, we can think of integration as being the area under the curve that's defined by the integrand. Essentially, we have a base, dx, times a height, f of x, and then we're going to sum up all the values of x possible from the endpoints a to b. This gives us an area. So whereas a derivative is analogous to a slope, an integral is analogous to an area. Now, we can have both definite and indefinite integrals. Definite integrals are things that show up, say, in the fundamental theorem of calculus here, where I have defined endpoints, a and b. An indefinite integral doesn't have endpoints. It gives us something called an antiderivative. So if I take the integral of a function, I get the antiderivative of that function plus a constant. That constant c exists because the antiderivative is actually a family of functions as opposed to just a single function, unless we know more about that antiderivative function. Whereas a definite integral asks this question: what is the area under the curve defined by the integrand between the points a and b? The indefinite integral asks this question: what is the antiderivative of the integrand? We'll be using both definite and indefinite integrals to solve problems in physics, and which one we use really just depends on the situation. Often we will use a definite integral because often we know what the endpoints or the definite points that we're evaluating the integral at are. But sometimes for more general solutions, we will just want to find the antiderivative of a function, which is when we'll use an indefinite integral. Like derivatives, integrals have nice properties and rules that help us evaluate them more quickly. Here are some useful ones. First, the integral of a sum is equal to the sum of the integrals. So just like derivatives, if I have a sum of two functions within the integrand, I can separate that into two separate integrals. This can make evaluating them easier. 2, I can pull any constant factor outside the integral. Again, this helps simplify things and works just like derivatives. If I have the integral of c times f of x dx, I can pull that c factor outside the integral and it becomes c times the integral of f of x dx. For functions that involve functions inside of other functions, I can use something called U-SUBSTITUTION. I basically define a new function, u, in terms of the inner function. This means that I also need to change my limits of integration if I'm working with a definite integral. We'll look at this on a case-by-case basis, but for now, think about this as analogous to the chain rule of differentiation. For functions that are multiplied together, what I can do is I can use something called integration by parts. This says that the integral of two functions multiplied together is equal to a boundary term minus the integral where those two functions are switched in their positions. Again, we'll go over this in a case-by-case basis and in future episodes, but for now, we can think of this as analogous to the product rule of differentiation. Now for some useful function-specific rules. The power rule of integration works similarly to the power rule of differentiation. The integral of a power function is equal to 1 over the power plus 1 times x to the power plus 1. I'm going to add 1 to the power and then divide the whole function by that power plus 1. The integral of a constant function is a linear function. 3. The integral of 1 over x dx is equal to the natural logarithm of the absolute value of x. This one pops up a lot because often we deal with relationships such that 1 over the variable is the relationship we're interested in. 4. The integral of the exponential function e to the x is simply itself, just like with the derivative. Now, if we're talking about the antiderivative, we might need to add a constant c to the end of it, but if we're dealing with a definite integral, we're just going to do e to the x evaluated at those endpoints. Now, this only works for the base e, but it can be generalized to other bases as well. 5. The integral of cosine is sine, and the integral of sine is negative cosine. And that's it. We'll cover more complicated integrals as we come to them, but these sorts of integrals and rules and properties should get you through most of what you need to accomplish, especially in a beginning physics course. In the next episode, we'll take a look at this problem, but in the meantime, why don't you try it out yourself? What is the area under the curve of this function, f of r is equal to 0.27 over r squared, evaluated from 0.02 to 0.05? Try it out yourself, and I'll see you in the solution.